everyone. I'm going to show you how to do some of these new math problems. We're going to learn a new equation today that has to do with the Doppler effect. So you just read about the Doppler effect and watched a video. So basically what the Doppler effect is, or it says that whenever something that's emitting light or any kind of wave, in this case, since we're talking about astronomy, we're going to talk about light waves. If something's moving away from you or towards you and it's giving off light, you perceive the wavelength of that light differently than if it were just stationary. So if something's moving away from us, if we see a star that's moving away from us, the wavelengths that we perceive are going to be longer than what they actually are. The wavelengths of light get stretched as the object moves away. When something comes towards us, those light waves get squished, so they become shorter wavelengths. So if you notice here, there's a red and a blue. The visible light spectrum red has long wavelengths. It's the color with the longest wavelength. Blue is the color with the shortest wavelength. So we call, when something's moving away from us, we call that a red shift because the wavelengths get longer. If something's coming towards us, we call it a blue shift because the wavelengths get shorter. So there's an equation we can use to figure out how fast something moves away or towards us. So that's what we're going to practice now. So if we were to look at a star using a spectroscope, you're going to see a spectrum of light, and you're going to see lines through that spectrum, and those lines correlate with a certain wavelength. Depending on what kind of gas is present in the star, you'll see a different pattern of spectral lines in its spectrum. We're going to do a lab with this pretty soon. But you see something that looks kind of like this. This is an example of a spectra with lines through it, spectral lines through it. So if this were a spectra of a star, a distant star that we're looking at, and it's moving away from us, then we're going to see all of those lines slightly shifted towards the red end of the spectrum. If that star was moving towards us, the spectral lines would look slightly shifted towards the blue end of the spectrum. So this is a red shift star example, this is a blue shift star example. Okay, so we can take how far that line has shifted and use it in an equation to figure out speed. Okay, so here's an example of where you would use that equation. So the spectral lines emitted from a distance, I'm going to change this to a star in a galaxy, in a different galaxy, are analyzed. One of the lines for hydrogen, so remember those lines correspond to an element that the star is burning, has shifted from 450 nanometers to 498 nanometers. Is the galaxy or star in the galaxy moving away or towards us? So we can answer that question. That's a pretty easy question to answer because you look at just the shift in the wavelength. It went from 450 to 98. That means it got longer. The wavelength is stretched, so that's a redshift. Redshift means the star is moving away from us. Okay, so it's moving away. And then the next question is how fast? What's the speed? So this is the equation we use for calculating speed. It's the speed of a star, that's our unknown, that's x, divided by the speed of light, which we know. We always know is 3 times 10 to the 8th meters per second, or c, which we used in our other equations we learned last week, equals, so it's a proportion, so that ratio is equal to the difference in the wavelength divided by the stationary value. So if we use numbers from this problem, this is what it looks like. Speed of the star, that's our unknown, divided by speed of light is equal to the difference in wavelength. So it went from 498 to 450, or 450 to 498. So to find the difference, you subtract those. Divided by the stationary value for wavelength. So the stationary value is always the first wavelength that was given. So that was the original value, it shifted to something else. So you could solve this part of the proportion first. To make it easier on the calculator, I would do that. I would take 498 minus 450. So that's 48. Divide that by 450. What do we get when we do that? 48. You get 0.11. So we're left with x over 3 times 10 to the 8 is equal to 0.11. So then to solve for x, you just need to cross multiply. So you take your 0.11 times 3 times 10 to the 8, and that will give you the speed of the star. About 3.2 times 10 to the 7th meters per second. So that star is moving pretty quick.